Okay, let's continue with AC circuit analysis. Okay, so at steady state. So in part 2, I will be doing simply the Thevenin and Norton Theorem, example from those. The session topic number 27 was 26 was quite long. Okay, so I hope you had a break. You can pause it anytime, right? Okay, so Thevenin Theorem. If you recall, let's recall this. Okay, Thevenin Theorem is a method to simplify your complex linear circuit to be represented by what is called the Thevenin equivalent circuit. Which consists of simply a voltage source, VTH, and the impedance, Thevenin impedance, ZTH, connected in series to it. Okay, so only these two elements. Before the midterm, it was simply, VTH and RTH, right? So, but now we have instead of R, we go into impedance. So, find examples for Thevenin. Find Thevenin equivalent circuit. External to RL. External to RL. So let's see. 5K ohms. Vs equal to 0 degrees volt. 10K ohms. RL, which is equal to 47K ohms, and this R is 10K ohms. So we want to find a Thevenin equivalent circuit external to RL, so anything except RL. Okay, so therefore the step, first thing you have to realize something is that, hey, how come my R is 10K ohms, looks fine, but my inductor, why is it only 5K ohms? And capacitor is 10K ohms, just like resistor. Okay. You have to, if you have a problem like this, you have to something's wrong. Okay. So the thing you have to do is, but we are in impedance, there's always a J in it. Okay. So always, if you encounter this problem, it means that this value is given to you 10K ohm is your XC, your reactant value, This is also XL. So therefore, when you analyze it, when you're really going to analyze it, you have to put the minus J in front and J in front of that 5K ohms also to make it impedance. So don't forget that. Okay. Because if we do this in class and ask you to find Z Thevenin, you guys are all wrong because you just take 10K, 5K, and 10K. Okay, and you can't do that. So first thing is you have to remove RL so that we will have an open circuit voltage. Yeah, remember, right? VTH is the open circuit voltage at the terminal that you want the answer, you want to look into, right? And ZTH is simply the total impedance looking into the terminal that you want to find the Thevenin. So in this case, we want to do anything external to RL. So therefore, we have to remove RL out first so that we get the open circuit. So therefore, you have J5K now, ohms, the voltage source, 50 degrees volt, capacitor minus 10kJ ohms. Take out, remove RL, so you have open circuit right here, VOC, and this is 10K ohms. Right? So now you have to find VOC. Your VTH is equal to V open circuit at that terminal. So write it down, terminal AB like this. So looking here, you should identify and say, oh, okay, VOC is nothing but the voltage drop across this 10K. So it's simply here, 10K, right? So this is VOC. You can even, if you're confused, or, well, I don't know if you can just do it like this too. Oops, what happened? Right? So VOC is voltage drop across the 10K ohms. Okay. Well, if I'm a current, I flow out from the source, right? Then I split into here and here. This current goes through minus 10 kJ, goes through this R. So these two are connected in series, right? They connect in series. Of course, if you think that, okay, then that means I can find I total split into this I1, right? And I1 times 10K, you get the answer. But then I realized if you are, I'll be happy if you can see that we didn't have to do that the long way, is that these two are connected in series. And this node right here, and this node right here, the voltage drop is 5, is 5 volt. And it's the same thing as the same node as this cover the capacitor and resistor connect in series. It's as if you have a circuit look like this. Can you see that? So this is your VOC and this is 5 volt. So you said you have one loop right here. This is one loop right here. And then your VOC divided out from the 5 volt. So you can apply voltage dividers. So therefore, see, it becomes 10K over 10K minus J 10K times 50 degrees. So therefore, your VTH is equal to 3.54 angle 45 degrees volt. Ta-da! See? Next, ZTH. Thevenin impedance, right? So, therefore, you would have the inductor 5jk ohms, right? And then ZTH is the total impedance, right? Look into the terminal with all the sources, turn off. So the impedance, if it's a voltage source, you short it. So short the voltage source. Okay, and this is minus J 10K ohms. And this is the terminal that you have to look into, Z total. And this is 10K ohms. Okay, so what do you see? So it's simply, if you imagine there's a current flowing through, current comes out from here, it go right here, right? This is short the 5 kJ out. So you have only minus J 10K, another current goes like this, so 10K. So these two are in parallel. So your Z total, your ZTH is equal to Z total equal to minus J 10K parallel with 10K. So equal to 10K times minus J 10K over 10K plus minus J 10K equal to 7.07 angle minus 45 degrees K ohms. So now you can draw your Thevenin equivalent circuit. So it consists of VTH, which is 3.54 angle 45 degrees volt, and the ZTH in series to it, right, which is 7.07 angle minus 45 K ohms, okay, AB right here, right? But then at the beginning you remove your RL out, you're supposed to reconnect it, put it back. So this is 47 K ohms, your RL. And then whatever you want to do with the circuit go ahead. Okay, so this is Thevenin circuit. All right, so next one is Norton. So Norton's Norton's. Okay, of course, more example will be, shown or taught online, okay, live online by me, okay, and we schedule that. Okay, this is how the course goes. So this is just for you to know all the theorems, okay, understand before we see each other, either online or in class, okay, because normally we supposed to, because of COVID, right, we have to do this. Okay, so now Norton Theorem. So Norton Theorem is a theorem that we represent our so-called complicated circuits with simply a Norton equivalent circuit. And our Norton equivalent circuit, okay, consists of a current source, IN, Norton Current, okay, and a Norton, I would say Norton Impedance, okay, connected in parallel to the current source. Okay, so let's see. So we're going to find the Norton, determine, so example for Norton, determine Norton's equivalent circuit as seen by the load resistor. Oh, and of course, the examples you can also find and search for yourself. Okay, either you go the traditional, conventional style, go to a library, get a textbook, or buy a textbook and look through examples at the back of the chapters. Okay, or you can even search from other YouTube, the professors, on YouTube. They have several examples and they explained to you also. So there are many ways that you can go about looking for self-exercises. Okay, there are books online too. Okay, so therefore you have to also help yourself by looking for problems to exercise and study. Okay, so let's continue. So example is, this is 60 0-degree volt, 50 ohms, 56 ohms, 100 ohms, RL. So we want to find Norton equivalent circuit, okay, seen by the resistor RL here, right? I can write this as terminal AB. Again, right, in this problem, the reactant is given to you. So therefore, before you analyze a problem, you should, make it an impedance by, it's a capacitor, insert minus J there. This is also a capacitor, put a minus J there. Okay, the resistor, nothing, leave it like that. So therefore, first remove RL so that you have an open circuit right there. So remove RL. So remove RL. Then to find IN, right? Norton current. Norton current is the short circuit current at the terminal. So therefore you short it, and this is your short circuit current, which is equal to the Norton current. Your choice how you go about finding it. You can use mesh, you can use nodal analysis, you can use dividers, simple dividers rule. Of course, I'm going to use a simple dividers rule, okay? So, well, IN has to come from somewhere. So I'm a current, I'm coming from the source. I'm going to call this IS, okay? Go through here, I split into here, and of course split into this I short circuit. So I'm going to find, well, my formula would be, right, to find I short circuit would be, hey, my short circuit IN or I short circuit divided out from the IS, right, divided out from IS, right, okay, and it divided into two branches, and I'm going to use this shortcuts formula, okay, so therefore it becomes 56, right, and the sum of the two impedance in the two branches, so 56 plus minus 100J. So this is my short circuit formula to find ISC or equal to IN. But before that I have to find IS, okay, so my IS is like a total current coming out from the source, so my IS is equal to the voltage source divided by Z total, right? So Z total is the total impedance looking from the voltage source point of view. So my Z total, looking into it, it would be this minus 100J parallel with 56, and the whole thing is in series with minus 50J. Okay, so it become minus 100J multiplied by 56 divided by 56 minus 100J, right, and then plus minus 50J. Using your calculator, your Z total becomes 42.6 minus J 73.9 or 85.3 angle minus 60.0 ohms. So therefore my IS is equal to 60 0 degrees divided by 85.3 angle minus 60 degrees. So the answer is 703 angle 60 degrees milliamps. And then I get my IS, I reinsert using these equations. So therefore my IN is equal to 56 over 56 minus 100J times 703 milliamps. So the answer is 344 121 degrees milliamp. This is my Norton current. Okay. So as for my Norton impedance, okay, so it's the same thing as the way you find Thevenin impedance. So it's a total impedance looking to the terminals with all the sources turned off, independent sources turned off. So therefore the voltage source you shorted, okay, and this is what you have. So looking into here, Z total is equal to, right, so 56 parallel with minus 50J, and then in series with minus 100J. So it's equal to 56 times minus 50J divided by 56 minus 50J minus 100J. So the answer Z total or equal to the Norton impedance is equal to 130.2 angle minus 79 ohms or 24.84 minus J 127 ohms. So therefore your Norton equivalent circuit would look like this. So this would be 24.84 minus J 127 ohms, and IN is 344 angle 121 degrees milliamps, and of course you reinsert your RL because you remove it out at the beginning. So this is the representative of your original circuit in the form of Norton circuit. Okay, so that's just to an example to remind you of the theorems that we use to analyze circuits. So that's it for the AC steady state circuit analysis. Thank you.